We're going to talk about fractional exponents today. Now, before we get into actually how to manipulate or to use fractional exponents, we're actually going to talk about what is a fractional exponent. Well, a fractional exponent is exactly what it sounds like. It's an exponent that's a fraction. But what you need to understand is that a fractional exponent is also a radical, just like what we have right here. A to the b over c is equal to the c root of a to the b power. Okay, so that's important for you to understand, is that a fractional exponent is just another way to write a radical, similar to how a fraction is just another way that you can write a decimal. So some situations it's more helpful to have a radical. Other situations it's helpful to have a fractional exponent. So let's do a little practice here. Let's convert a couple of these into radicals. So x to the 3 over 2, so the bottom number, the denominator, becomes the index and becomes x to the third. Now you don't really have to write the 2. Remember, if they're anytime we have a square root, there's a 2 there, but you don't have to write that. Now you should simplify this. So this would simplify to be x root x. Okay, let's try the next one. Again, the bottom one goes on the outside, so it becomes a 4th root of x to the first. Writing the index is really important when you're dealing with a number that isn't 2. Okay, that's really important. If there isn't a number written right here, the assumption is that it is a 2. So there's a big difference between a 4th root of something versus a square root of something. So that's really important. One last one. Let's try this one right here. So I'm going to write it as the cube root of x to the 4th. So the cube root of x to the 4th, let's see, would be x cube root x. And there you go. Simple as that. So converting to radical notation isn't incredibly difficult, but things can get kind of complicated. Let's take a look at this problem here. It says simplify and leave an exponential form. All right, well, it would be nice if I knew what the 2 to the 1/3 is, or what 2 to the 2 or 16 to the 2/3 is, but I don't. So we should be able to simplify it somehow. Well, what I do notice is that 16 has a factor that is common to 2. As a matter of fact, it is 2. 2 is a factor of 16. So I can rewrite this. I'm going to rewrite it as 2 to the 1/3. This 16, I can write that as 2 to the 4th power. 2 to the 4th is the same thing as 16. Now it's all to the 2/3. And then now rules of exponents tell me that I should be multiplying those. So it becomes 2 to the 8/3. Okay, now the whole reason for that is because we have this 2 and we have this 2, and because we have the same base, remember rules of exponents said that if I had the same base and it's multiply in between, I can add my exponents. So that means I can change this. This would be 2 to the 9/3, or 2 to the 3rd power, which we know is 8. And there you go. We're able to simplify this fairly complex thing right here down to where it actually is equal to 8, just by changing this base to something that's similar to this base. So let's take a look at the second one. Second one is pretty similar. You notice here that 5 is the common factor. So I'm going to rewrite 25 is 5 squared. So now this right here would become 5 to the 1/4 times 5 to the 2/8. But we know 5 to the 2/8 is the same thing as 5 to the 4th. And as long as my bases are the same, they have to be the same, I can add them together, the exponents that is. So 1/4 plus 1/4 is a half. Now this time there's nothing that I can do. I don't know what 5 to the 1/2 power is, and the instruction said simplify and leave an exponential form. So there you go. This would be a reduced form of what that is. Okay, hopefully that makes sense. So let's keep moving on. What about a scenario like this? Now, the instructions here are pretty easy. They just says evaluate. So we're just trying to figure out what the heck this thing equals. Now, I understand you could use a calculator for some of this. Many calculators will be able to let you do fractional exponents. But let's just go with the idea that you can't use a calculator. So how would I figure this out? Well, I don't know what 8 to the 2/3 is. So what I could do is this. I could change this to radical form. And that would be to the 3rd root of 8 squared. Now, 8 squared, you can do it one of two ways. One, you can think of it as 8 squared is just 64. And this cube root of 64 is 4. And I'm done. Another way that you could have done it, instead of going this route, another way you could have done it is you could have said, oh, well, this 8 squared is 8 times 8. The cube root of 8 is 2. The cube root of 8 is 2, which then is 4. Okay, so two different ways that you could have done that problem right there. And that happens a lot. You go through and do some of these, and somebody might do it one way, another person might do it the other way, and you come up with the same result. Not a problem. Okay, let's take a look at the next one. Notice this should kind of ring familiar to what we were just doing. This time, though, notice that I have common bases. So I can actually put those together. So I can write that as 4. Now, 3/4 plus 1/2 would simplify to be 5/4. Now, I don't know exactly what that is, but let's see if we can simplify it a little bit. Maybe I can. So I get the 4th root of 4 to the 5th. And now the 4th root of 4 to the 5th would be just simply 4 4th root of 4. So lots of 4's right there. Now, to be honest, it didn't say evaluate and tell me or write it in simplest radical form or anything like that. So technically, you could have just left it right here. And since we don't know what 4 to the 5/4 is, you could have left it right there. If you wanted to leave it in radical form, I guess you could have left it like that. If you had a calculator, then you would just type in 4 to the 5/4. So that one didn't simplify out quite as nice as this previous one. Okay, so let's try one more. Maybe this one will simplify a little bit nicer than that last one. Okay, so this one says 27 to the 6/4 to the negative 1/3. So remember, this negative part right here is telling me that we're going to have to flip my fraction. So it's going to become 64 over 27 to the positive 1/3. And since the whole thing is to the positive 1/3, that means I could change it to the cube root of 64 over 27. And the cube root of 64 is 4. The cube root of 27 is 3. So that one works out really nice. Okay, nice and simple right there. Hopefully that wasn't too difficult. Maybe this only challenging part was recognizing the fact that it said negative, so you had to flip it over. Okay, last thing we're going to talk about in terms of dealing with fractional exponents. Okay, this one says express in simplest radical form. So you might be thinking to yourself, well, if it says simplify in simplest radical form, then why is this part of the fractional exponents part? Well, as I take a look at this, you notice this is a square root and this is a cube root. So you can't combine those together. The indexes are different. However, if I were to change this square root of 2 to a fractional exponent, and if I were to change this one to a fractional exponent, so we get 2 to the 1/2 times 4 to the 1/3. Now it becomes similar to what we just got done doing a section or two ago. Is there a way for me to combine these together? Yes, there is. I could rewrite 4. 4 is the same thing as 2 squared. So I get 2 to the 1/2 times 2 to the 2/3. And then I would add 1/2 times 2/3. 1/2 and 2/3. And if I did that, I'd end up with 2 to the 7/6. So, I'm not done yet though, because it says simplifying or express in simplest radical form. We're in fractional form or fractional exponent form. So I'm going to convert it back. So it'd be the 6th root of 2 to the 7th. And then I'm going to find the 6th root of 2 to the 7th. Well, that would be 2, 6th root 2. And there you go. I put it all together. All right, well, let's take a look at another one. This one, kind of funky looking, says the cube root of the square root of 27. Well, what the heck to do there? Well, let's look at it in terms of fractional exponents. Maybe it'll look a little easier or make a little more sense. So the square root of 27 would be this, 27 to the 1/2. And then the cube root of that would be to the 1/3. So the square root, cube root. So if I put those together, that would say 27 to the 1/6. Well, that's fairly easy. Now, what you might be thinking is this. Well, I can then just turn this to the 6th root of 27. And I'm done, because there isn't a 6th root of 27. You're correct. There isn't one. But the problem is this is not in simplest radical form. How do I know that? Because what I know is that 27 is the same thing as 3 to the 3rd power. So saying 27 to the 1/6 is the same thing as saying 3 to the 3rd to the 1/6. And so from here, if I combine those, 3 times 1/6 becomes 1/2, and it becomes the square root of 3. This is the simplest radical form, not this. Okay, so you need to keep track of things like that. When it says simplest radical form, it means the smallest index. So you have to pay attention to numbers like 27, 8, 64, ones that are multiples of 2, 3, 4, 2 to the 3rd, 3 to the 5th, numbers like that, and see if you can reduce, because you should always try and reduce this. Okay, and the square root of 3 is much simpler than the 6th root of 27. We can kind of have a general idea of what the square root of 3 looks like. The 6th root of 27, a little more challenging. Okay, so when it says simplest radical form, we are referring to what's the smallest index that you can write. Okay, let's see. Let's do this last one, and we'll call it a day. So this one says a to the 1/4, b to the 1/2, 2 to the 5/6. And we're trying to combine this into the simplest radical form. Now you'll notice this is a little different than this one we did up here, because here I was able to change 4 to a 2 and we can combine them together. But the problem is that now we're dealing with an a and a b and a 2. We can't change those bases to be the same. So here's another strategy that we can do. Is what if I were to change all my fractional exponents so they had common denominators? So instead of a to the 1/4, write it as a to the 3/12. Instead of b to the 1/2, b to the 6/12. And 2 to the 10/12. Now, why would I do that? Well, the reason why I would do that is because this is the same thing. Now, this is a little bit of an unnecessary step. I'm going to write it anyways. Okay, these mean the same. And our rules of radicals say that as long as my indexes are the same, I can multiply these together. So it all becomes the 12th root. I'm going to put the number first, 2 to the 10th, a to the 3rd, b to the 6th. Which, if I really wanted to multiply out, 2 to the 10th is, I believe, 1,024. Okay. And there isn't anything more that I can do. I can't simplify this more. I can't lower my index anymore. There isn't a cube root of 1,024. There isn't a cube root of a to the 3rd or b to the 6th. So we're done, and we simplified it into simplest radical form. The difference being on this one, though, is the fact that we couldn't change a, b, or 2 into the same base versus a problem like this one where I could change the 4 into a 2. Okay, and then I added my exponents. When I can't change those bases, I change my fractional exponents into the common denominator and then put them together. Okay? So that's it for fractional exponents. A little bit of manipulation there. Hopefully it all made sense.